Section: Introduction. In this section, we have discussed the importance of temporal localization in video large language models, LLMs. These models have shown great potential in understanding instructions across various modalities like images, videos, and audio. However, existing video LLMs struggle with accurately pinpointing time periods in videos when asked "when" questions. This limitation stems from issues with how time is represented, the architecture of the models, and the lack of emphasis on temporal localization in the training data. To address these challenges, we introduce our solution called Language Instructed Temporal-Localization Assistant, LITA. Firstly, we propose using time tokens to represent relative timestamps instead of plain text, allowing for better communication about time in videos. Secondly, we introduce SlowFast tokens to capture temporal information at a fine resolution, enabling precise temporal localization. Lastly, we emphasize the importance of temporal localization data by introducing a new task called Reasoning Temporal Localization, RTL, along with the dataset ActivityNet RTL. Our approach involves dividing a video into equal chunks and introducing time tokens to represent the relative time location in the video. This relative representation simplifies encoding and decoding of time information compared to plain text timestamps. We also address the challenge of processing a large number of frames efficiently by using a combination of fast and slow tokens inspired by the SlowFast architecture for videos. Furthermore, we enhance the training data for LITA by including dense video captioning and event localization tasks with annotated timestamps. Additionally, we introduce the RTL task, which requires temporal reasoning and world knowledge to answer questions accurately. By focusing on temporal understanding, LITA not only improves temporal localization performance but also enhances the core capabilities of video LLMs. Our experiments show that LITA outperforms existing video LLMs in terms of temporal metrics and reasoning capabilities. It achieves a significant improvement in correctness of information and temporal understanding on a video-based question-answering benchmark. Section Summary. In this section, we introduce the concept of video large language models, LLMs, and highlight the importance of temporal localization in these models. We address the limitations of existing video LLMs by proposing Language Instructed Temporal-Localization Assistant, LITA, which focuses on improving time representation, architecture, and data to enhance temporal understanding and reasoning capabilities in video processing tasks. Our approach significantly boosts performance metrics for temporal localization and overall video-based question answering, showcasing substantial advancements over current video LLMs. Section: Related work. In this section, we explore how different approaches have been used to enhance large language models, LLMs, for handling tasks that involve both text and images or videos. Some methods involve modifying the LLMs by adding new components like gated cross-attention layers or adapter layers to help them process both text and visual information. Others focus on using separate modules, such as projection layers, to translate visual data into a format that the LLM can understand. Recent studies have expanded these multimodal LLMs to tackle tasks like visual grounding, which involves tasks such as object detection and segmentation. One relevant study is LITA, which extends the concept of segmenting objects to segmenting reasoning processes. Our approach, called Reasoning Temporal-Localization, builds on this idea by combining reasoning and understanding temporal sequences. Moving on to video models, researchers have extended image-based LLMs to handle videos as well. These models typically involve converting visual data into a format that the LLM can process, often using projection layers or Q-formers. While these models have shown promise in tasks like answering questions about videos, they still struggle with accurately pinpointing events in time. Our model, LITA, aims to address this limitation by improving the temporal localization capabilities of video LLMs. By incorporating elements like relative time representation, SlowFast tokens for capturing detailed temporal information, and multitask training, LITA can better understand and pinpoint events in videos over time. We will now provide an overview of the architecture of LITA and delve into the specifics of its components. Section Summary. In this section, we explore how large language models, LLMs, are being adapted for multimodal tasks by incorporating additional parameters like gated cross-attention layers or adapter layers. Some approaches focus on using projection layers or Q-formers to integrate visual information into LLMs for tasks like visual grounding. Our work, LITA, enhances video LLMs by introducing reasoning temporal localization to improve temporal understanding and reasoning capabilities, addressing the limitations of existing models in temporal localization tasks within videos. Section: SlowFast Visual Tokens. In this section, we have explained how we divide time in videos into T steps to enhance video ILM's ability to understand time. To effectively process time, the visual input must match this time resolution T. It is ideal to have at least T frames to pinpoint events accurately within this resolution. However, directly inputting all T frames into the LLM module could be computationally demanding. In our study, we set T equals 100 and M equals 256, clip vid L14, resulting in 25,600 tokens per video. Drawing inspiration from SlowFast models, we explore two pathways to combine the T times M tokens for T frames. The first pathway involves densely sampled fast tokens to capture temporal information. We derive T fast tokens from T frames by averaging the tokens within each frame. The second pathway includes sparsely sampled slow tokens to preserve spatial information. By selecting a spatial downsampling ratio of S, we choose S² frames uniformly from the video. For each selected frame, we apply AS times S spatial average pooling to the M tokens, resulting in frac M S² slow tokens per frame. This strategy yields a total of M equals frac M S² times S² slow tokens. In our experiments, we set S equals 2, leading to a total of T plus M tokens to represent a video instead of T times M tokens. Regarding training tasks, in addition to architecture, the choice of training tasks and data significantly impacts the performance of LLMs. We highlight the importance of temporal localization data and train LITA with 5 tasks: dense video captioning, event localization, video question answering, natural language visual question answering, and our proposed reasoning temporal localization. Temporal localization is crucial for 3 of these tasks: 1, 2, and 5. We introduce each task sequentially. The first 3 tasks are standard video tasks that enhance LITA's fundamental video understanding. 1. Dense video captioning. Each video is described by sentences with corresponding start and end timestamps of events. These sentences are sorted by start time and concatenated. An example prompt for this task is to provide a detailed description of a video with sentences starting with timestamps. 2. Event localization. The aim is to temporally locate events described by sentences using a simple format of start and end timestamps. An example prompt asks when a specific event happens in the video. 3. Video question answering. Questions are posed as language instructions, and answers are typically short. To provide context for short answers, a prompt instructs to answer using a single word or phrase. Training LITA with these tasks enhances its video understanding capabilities. However, to improve natural language conversation abilities, we also incorporate natural language visual question answering datasets. Mixing instruction tuning datasets with standard video tasks enhances LITA's conversation quality while maintaining good video understanding. Finally, we train LITA with our reasoning temporal localization task, which involves providing timestamps and explanations for reasoning in answers. This task leverages LITA's reasoning and temporal understanding capabilities to enhance its performance. Section Summary. In this section, we focus on enhancing video ILM's temporal reasoning by introducing SlowFast visual tokens. We discretize time into T steps to improve temporal processing, using T equals 100 and M equals 256 tokens per video. By pooling fast tokens for temporal information and slow tokens for spatial details, we reduce the total tokens needed to represent a video to T+m. Additionally, we emphasize the importance of training tasks like dense video captioning, event localization, video question answering, natural language visual question answering, and our proposed reasoning temporal localization to enhance ILM's capabilities in understanding videos. Section: Problem Definition. In this section, we define the problem of reasoning temporal localization. When reasoning about temporal localization, we are essentially answering a when question that involves determining the start and end times of an event. The unique aspect here is that the specific event in question is not explicitly mentioned, requiring the model to infer it based on reasoning and its knowledge of the world. Therefore, the answer to such questions includes providing the start and end times of the event as well as explaining the reasoning process followed by the model to derive these timestamps. Several examples are illustrated in the dataset to clarify this concept. Our dataset, ActivityNet RTL, is designed for the reasoning temporal localization task. It is created based on the ActivityNet Captions dataset, which annotates various events described in video sentences with their respective start and end times. For instance, if a video shows a woman standing, dancing, and then sleeping within specific time intervals, we can ask a question like, when is she the least active? This question requires reasoning to identify the time period when the woman is sleeping, which is the least active among the mentioned activities. To train our model, we utilize the data generated by GPT-4 on 10,009 videos from the ActivityNet Captions training set, resulting in 33,557 question-answer pairs for reasoning temporal localization. While most questions generated by GPT-4 are valid for temporal localization, some do not necessitate reasoning as they directly relate to events described in the video captions. However, we include these questions in the training set with the expectation that our model, LITA, can also answer standard temporal localization questions accurately using natural language. For the evaluation set, manual curation is essential to filter out non-reasoning questions. We begin with GPT-4 generated questions from a subset of the ActivityNet Captions validation set and manually remove questions that do not require reasoning. Additionally, we verify the timestamps and explanations in the answers to ensure accuracy. This process results in 229 question-answer pairs for 160 videos in the evaluation set. In evaluating the ActivityNet RTL dataset, we consider three metrics: MEO, precision at 0.5, and GPT-4 relative scores. The first two metrics assess temporal localization accuracy, while the third metric evaluates the quality of explanations provided. MEO calculates the average intersection over union between predicted and ground truth timestamps, while precision at 0.5 measures the percentage of predictions with an IOU over 0.5. To evaluate the explanations, we leverage GPT-4 to assess their helpfulness, relevance, accuracy, and level of detail, assigning a score from 1 to 10. The scores for predicted explanations are normalized against the ground truth scores. Section Summary. In this section, we define the problem of reasoning temporal localization, RTL, where queries involve determining the start and end timestamps of an event without directly mentioning the event itself, requiring models to infer based on world knowledge. We introduce the ActivityNet RTL dataset, derived from ActivityNet Captions, to train models to generate questions that demand reasoning for temporal localization. Our training set comprises question-answer pairs generated by GPT-4, aiming to enhance the model's ability to reason and provide explanations, while the evaluation set is manually curated to ensure the questions focus on reasoning. Section: Experiments. In this section, we assess LITA's performance on tasks involving temporal localization and video tasks that do not require temporal localization. This is important because most existing video LLMs struggle with temporal localization. We also test LITA on a video-based text generation performance benchmark to get a comprehensive understanding of its capabilities as a video LLM, not just for temporal localization. Regarding the implementation details, we sample 100 frames from a video and use 100 time tokens numbered from 1 to 100 to represent timestamps. We utilize clip L14 as the visual encoder and Vicuña as the LLM module. Following Java's architecture, we train a single linear layer for projection. We incorporate 4 frames for slow tokens and apply an average pool window with a size of 2. By including 1 fast token per frame, we end up with a total of 356 tokens per video. For the training datasets, we use ActivityNet captions and uCook2 for dense video captioning and event localization tasks, NextQA for video question answering, LLAVA 150K for image instruction tuning, and ActivityNet RTL for reasoning temporal localization. We randomly select 100K samples for each of the 5 tasks, totaling 500K samples. The training is carried out with a batch size of 128 and a learning rate of 2E5 for 4K iterations, taking around 13 hours for 13B models and 9 hours for 7B models using 8A100 GPS. In evaluating reasoning temporal localization, we use the newly proposed ActivityNet RTL dataset. We measure precision at 0.5 and GPT evaluation score for explanations. We compare LITA with Video Llama v2 and Video Chat GPT, observing that LITA outperforms them significantly. We also analyze different variations of LITA, such as slow tokens only, SlowFast tokens, and the full LITA model in 7B and 13B sizes. The results on ActivityNet RTL demonstrate that LITA surpasses all baselines in performance metrics. It provides detailed and accurate explanations, as shown in qualitative results. Interestingly, we find that the temporal localization quality of LITA improves as we scale up the model from 7B to 13B, indicating that scaling the model enhances not only language understanding but also temporal reasoning for video LLMs. Section Summary. In this section, we evaluate our model, LITA, on various video tasks, including temporal localization and video-based text generation, to showcase its versatility as a video LLM. We implement LITA by sampling 100 frames from a video, using time tokens for timestamps, and training it on diverse datasets like ActivityNet captions and uCook2 for tasks such as dense video captioning and event localization. Through our evaluations, we demonstrate that LITA outperforms other models in reasoning temporal localization, providing detailed and accurate explanations, with its performance scaling with model size from 7B to 13B. Section: Video-based generation evaluation. In this section, we evaluated our model LITA using a video-based generation evaluation method to compare it with other video LLMs. We utilized a benchmark proposed by Moz that selects videos from ActivityNet and provides question-answer pairs in natural language. This benchmark differs from others by including specific and generic questions to assess aspects like correctness of information, detail orientation, contextual understanding, temporal understanding, and consistency in the answers generated by video LLMs. We compared LITA with existing models like Llama Adapter, Video Llama, Video Chat, and Video Chat GPT. Our results showed that Video Chat GPT performed slightly better than other baselines, including Video Llama v2. However, LITA outperformed these models significantly in all aspects, with a 22% improvement in correctness of information and a 36% relative improvement in temporal understanding. We believe that emphasizing temporal understanding during training not only helps in accurate temporal localization but also enhances the overall video understanding of LITA. This focus on temporal localization allows the model to grasp more details from videos, leading to improved comprehension. Similar improvements were observed in image LLMs when joint training with grounding tasks was employed to enhance text generation. Furthermore, we analyzed the impact of different training tasks on our model. We divided the tasks into 3 groups: RTL, Reasoning Temporal Localization, Video, Standard Video Tasks, and NLVQA, Natural Language Visual Question Answering. Training with all tasks, including RTL, Video, and NLVQA, resulted in the best performance for LITA. By incorporating NLVQA, which includes complex reasoning questions, LITA showed enhanced reasoning capabilities and could provide answers in natural language instead of short phrases.